Yeah, over to Asta, please.
Good evening, everyone. Welcome to the third event of the Curryley Days 2024 and to our second session of the day. Today, we have the honor of hosting Dr. Rishi Vyas, a distinguished mathematician with a deep expertise in algebra. Dr. Vyas' academic journey began with St. Stephen's College, where he earned an honors degree in mathematics. He then continued to the University of Cambridge for the graduate and doctoral studies. His thesis in Cambridge dwelled into homological aspects of the non-commutative ring theory. For his postdoctoral research at Ben-Gurion University of the NIC, Dr. Vyas further explored homological theory within the non-commutative ring. Additionally, he has also conducted significant research in group theory. For those who have questions, please raise your hands and one of the hosts will invite you to ask them. YouTube viewers can post your questions in the chat and we will convey them to the Dr. Vyas. With that, I'll please hand over the session to Dr. Vyas and yep, over to you, sir.
Thank you, Asta, for that very kind introduction, and big thanks to all of the organizers for the invitation to speak here. Let me just begin by sharing my screen. This is always a point where one hopes things work. Okay, so full screen visible to everybody?
Perfect.
Okay, great. Again, thanks to all of the organizers for the invitation to speak. My talk today is essentially three smaller talks, one very, very small. It's not particularly heavy, and I think given that this is a Sunday evening, what I'm going to do is spend about half of my time giving a pretty detailed introduction to the history of how some branches of ring theory emerged. So in particular, we'll talk about the first example of a non-commutative ring that was encountered, the Quaternions. And then we'll sort of take a dramatic change in tone and talk a little bit about how the theory of commutative rings has a geometric flavor associated to it, before ending with a very brief discussion of some of the pathologies that arise in trying to generalize that theory to the non-commutative context. Okay. Now, I presume most people in the audience have seen what a ring is, but just to get things started, in some sense, the most basic fundamental example of a ring is the integers. It is the initial object in the category of rings, but we don't need to know what that means. And it has a structure that we're all familiar with, right? There are two binary operations that are defined on it, addition and multiplication. And those operations satisfy a number of properties. And the fact that addition and multiplication are associative, are commutative, that you have additive and multiplicative identities, that multiplication distributes over addition, and that you also have an additive inverse for everything. If we move from the integers to the real numbers, we can essentially everything that we've said continues to hold. And in addition, we also have the following additional property that now not only do we have additive inverses for everything, but every non-zero element also has a multiplicative inverse. So if we take these properties that we've seen and try and formalize them as the basis of an abstract definition, what we get is the definition of a ring. A ring, broadly speaking, is a set equipped with two operations which model addition and multiplication. And the axioms that you require those operations to satisfy are essentially those that we saw for the integers, with the one exception that we do not require multiplication to be commutative. We do insist on a multiplicative inverse, so all of our rings are unital, but we don't require multiplication to be commutative. We do require addition to be commutative, but in fact, I mean, it's a nice exercise to show that in the presence of the remaining axioms on this slide, you don't need to assume that addition is commutative. You can prove it. It follows as a consequence of the remaining facts. So in particular, if we do insist that multiplication is commutative, we get commutative rings. If we, in addition, insist that your multiplicative identity is distinct from your additive identity, the only ring where this is not the case, where they coincide, is the zero ring. If you require them to be distinct and you, in addition, require every non-zero element to have a multiplicative inverse, then you get a field. So amongst the two examples that we've seen, Z is a commutative ring, R is a field, Z is not a field. Now, the definition that we just mentioned is a little bit over 100 years old. Even though, as we're going to see very shortly, the ideas that are sort of encoded in the definition, that you have these two operations that have a certain relationship, I mean, they were present for a good 70, 80 years before the definition of a ring was finally formalized. But the first formal definition of a ring in the way that we would be accustomed to it today is something that, dates from around the 1910s, 1917 to be precise, which is a good 30 years or so after I think groups were first defined formally. We've seen two examples already, the integers and the real numbers, and it's not too difficult to sort of see that the rational numbers also form a field. The natural numbers don't, because you don't have additive inverses. We'll see many more over the course of this talk. Okay, let's continue. Suppose instead of looking at R, I wanted to look at R2, right? And for me, R2 is thought of, to think of R2 not as just a set, but as the vector space R2. So you have you already have an additive structure, and you have, in some sense, have an action of R on this object. Now we can define an addition and multiplication pointwise, where you define both of these in terms of the individual coordinates. And indeed, if you do this, what you get is a commutative ring. And this is nothing special or particular to this case. If you take any two rings and you take their Cartesian product, it's easy to show via this exact definition that that Cartesian product can be endowed with the structure of a ring by defining these operations pointwise. Just to sort of isolate some specific aspects of the definition, the additive inverse is 0, 0. The multiplicative inverse for this operation is 1, 1. However, it's easy to see that this is not a field, right? It's not a field because anything which has a 0 as one of its coordinates can't possibly have a multiplicative inverse. In particular, there's nothing that I can multiply 1, 0 with to get 1, 1, because that second coordinate will kill whatever it hits. But we can also do the following. Instead, there is another multiplication that we can define on R2. And I mean, I formally described it by what's written in red on this screen. For some of, I mean, for many of us, it'll be very clear what this is encoding. But just thinking of it as a formal definition, it's not difficult to see that indeed it is associative. It's a irritating but straightforward computation. It's again not difficult to see that it is commutative. Again, just a straightforward calculation. The additive structure, of course, is the one that's defined pointwise, so I won't even talk about that. There is a multiplicative identity, which is 1, 0. Again, a straightforward calculation. And I suppose this last point really gives the game away if you still haven't sort of guessed what this object is. For every non-zero element in R, and by non-zero, I mean that at least one of its coordinates is non-zero, you can find a multiplicative inverse. And explicitly, that inverse is given by the following expression. At this point, sort of like lights of recognition go off in our mind, because we realize that what we've just seen is actually a familiar object. First, if we identify the real numbers with all of the elements of R2 which have 0 as their second coordinate, then multiplying by that corresponding element is just scalar multiplication in the vector space. If I multiply BC by A, 0, I get AB, AC. The second fact that we observe is that if I were to multiply 0, 1 with itself, I get -1, 0, which I can identify as 0. And if I call 0, 1, I, what we've just shown could be summarized by saying that I squared is equal to -1. And finally, if I take any two elements of R2, I can write it as a sum of, A, B is A, 0 plus 0, B, which we can now think of as A plus IB. So in other words, what we have just done is define the complex numbers. The vector space, the set should be a vector, sorry, that's a typo. The vector space R2 equipped with the multiplication that we've just defined is often taken to be the formal definition of the field of complex numbers, and it is indeed a field. It's easy to check that those axioms hold. In fact, we have already briefly seen that most of them do. Okay, good. So R is taken care of, R2 is taken care of. There's no reason to stop, so we can go to R3 and let's ask ourselves whether we can do a similar sort of process over here. Now, addition poses no problem, right? Because I really want to I don't want to mess around with the vector space structure of R3. I mean, as a set, fine. It's an uncountable set. You can take any other uncountable set and lift operations, but let's really pin down the vector space structure. So you don't want to change addition. You want addition to be pointwise. You, in some sense, want to recover the scalar multiplication on R3. And the question is there some multiplication which turns R3 into a ring in such a way that the vector space structure is recoverable? If you define multiplication as just pointwise multiplication, then sure, that works. But what you don't get is a field. The same issue that we had with the pointwise product on R2 continues to hold. This is a commutative ring. It is not a field. Okay, so we can try something else. There are other products that we have encountered on R3. I mean, there's, for example, the cross product that many of us might be familiar with from, I don't know, high school maths or high school physics. But this is not the kind of product that we're looking for. One thing that we learned, for example, is that the cross product is not associative. So it does not give us an associative algebra. It is not unital. In fact, any element crossed with itself is 0. It is a very interesting structure. I mean, the R3 equipped with this operation forms another kind of algebraic object called a Lie algebra, but it is not what we're looking for in this case. So we can continue. And if you try to come up or cook up algebraic potential multiplications on R3, which turn it into a field or a ring in which you have inverses, it's actually quite tricky. And just like now, let's take a step back into history, maybe 180 or so years ago now. The same problem was something that this person, William Rowan Hamilton, who was a 19th century mathematician, many of us would have heard his name in the context of theorems like the Cayley-Hamilton theorem, was thinking about. And there's a nice so I think there's a record of his collected papers somewhere. And there's a nice sort of excerpt where apparently, so the question of defining associative algebra structures on R3, not using that language, but just, figuring out how to multiply triples of numbers was clearly something that he was concerned with, because if you read sort of his papers, there's a letter in there from him to his son, where he sort of says that every morning in the early part of the above cited month, I think we know what the above cited month is, and we'll come to it in a moment. On my coming down to breakfast, your then little brother, whatever the brother's name was, used to ask me whether you can multiply triples, and he used to say that I can't. So it is something that he was trying to do. Hamilton's sort of major insight was that, okay, maybe triples are posing to be a problem. But if you move to R4, then suddenly you can say something. We, of course, as before, we don't want to damage the vector space structure of R4. So you define your addition to be pointwise. And what Hamilton proved was that if you take the following multiplication on R4, which looks a bit formidable, but there's a way to make it a lot more understandable, which we'll talk about in a minute, then what you get, you do get an associative operation which satisfies what we would today call the ring axioms, and in which you also have inverses for non-zero elements. More precisely, it's not a difficult thing to check that, so again, these are laborious but straightforward calculations, particularly the associativity. And if you take a non-zero quadruple, then you can find something which serves as a multiplicative inverse. And the formula or the explicit description is quite reminiscent of what you would do for the complex numbers. It's just that you have more things to work on, but it's essentially the same idea. So this does define the structure of a ring on R4, and you can recover the vector space structure of R4 from this. There is a slightly easier description to make sense of what's going on, which is that I can think of R4 as the real numbers cross R3, right? Via the standard correspondence, sending a 4-tuple to the pair consisting of a single scalar and a vector in R3 or a 3-tuple. And under the above isomorphism, we can reinterpret the multiplication that we defined previously as follows. that if we think of an element of R4 as a real number alongside an element of R3, and we have another such pair, so S is in R and W is in R3, then the multiplication that we defined on R4 is nothing but the following expression, where the dot is the dot product on R3, the cross is the cross product on R3. So this makes sense in terms of its syntax, right? The dot product of two elements of R3 is an element of R, so you can subtract it from RS. You can scalar multiply elements of R3 with elements of R. So RW and SW, I mean, RV and SW make sense. And the cross product of two elements of R3 is again an element of R3. So you can add those last three things up. And if you just sort of work out the formulas, that's exactly what the multiplication in Hamilton's construction is doing. And using this interpretation, something which Hamilton observed becomes readily apparent, which is that suppose we take along the same way that we defined I to be 0, 1 for the complex numbers, we define I, j, and k as the following quadruplets. Then first, what we again see is that if I identify R with those quadruples which have 0 in the second, third, and fourth coordinate, then multiplication by R recovers the scalar multiplication coming from the vector space structure of R4. Second, a calculation that is very straightforward once you've observed this fact about how you can break down the multiplication in the Quaternions in terms of the cross product and the dot product, tells us that I squared is equal to j squared is equal to k squared is equal to -1. And finally, finally, we have the following collections of equations. The way to make sense of I, j, k is to really sort of think about the cross product in that if you think of I as 1, 0, 0, 0 and j as 0, 1, 0 in R3, then k is just their cross product in R3, sitting back inside R4 via the isomorphism that we talked about. What that also reveals, before we talk about what that reveals, so apparently Hamilton struck upon the idea of defining this multiplicative structure while out on a walk in Ireland, where he lived. And the story goes that he was crossing this bridge. I didn't take this picture. This was I found on Wikipedia. And while walking across this bridge, he was suddenly struck by the insight that if you defined a multiplication on R4 in the way that we just discussed, then you get an associative. Well, he wouldn't have called it an associative algebra, I think, but you get something which resembles a number system. If you look in this picture, there's a sort of this gray square on the bridge. And apparently, if you go there and zoom in, it sort of records the fact that Hamilton discovered this object while walking across this bridge. I think the plaque says here, as he walked on the 16th of October, 1843, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for Quaternion multiplication. And then the IJK over here, the IJK that we talked about as well, and cut it on the stone of this bridge. These four expressions are enough to determine the total product, because then you just assume that I, j, k, and 1 are the basis of a four-dimensional vector space, and then you just expand your product linearly, and this is what you get. Now, one observation is that, again, and this becomes very clear when we think about the cross-product interpretation, ij is k, but ji is -k, right? Because flipping the order of the cross product negates the element. In one direction, you're sort of getting, if your elements are linearly independent, the cross product picks out an orthogonal element in one direction, negating it gives you it in the opposite direction. But this is also just immediate from the formal definitions if you prefer to work them out. And Hamilton's construction was the first example of a non-commutative associative operation. Today, we would call, so the Quaternions are denoted by H in honor of Hamilton. Today, we would call H a division ring. A division ring is a ring in which 1 is not equal to 0, and every element which is non-zero has a multiplicative inverse. This may look familiar, it should, because fields are precisely those division rings which also happen to be commutative. Okay. There is another example of a non-commutative associative operation that we also encounter, which you can also define on R4. It's not going to be a division ring, and thus matrices. Matrices, interestingly, seem to have been discovered a little bit after the Quaternions. I think the first recorded instance of matrix multiplication being defined is by this person, Arthur Cayley, who is the other name that's associated to the Cayley-Hamilton theorem. And I think there is this sort of excerpt from a paper that Cayley wrote in the 1850s, where if you just read what he's writing, he's basically observing that matrices have an addition and a multiplication that behaves in the same formal way as addition and multiplication for ordinary number systems, with the exception that multiplication is not commutative. I think the exact phrase that he uses over here is that there is a peculiarity that matrices are not in general convertible. The rest of this paragraph goes on to actually state in some form the Cayley-Hamilton theorem. So I suppose that's where it comes from. Okay. And of course, we know what matrix is. These are the defining equations for matrix for multiplication for 2x2 matrices, something that I'm sure most of us are familiar with. What about Hamilton's original question? Right? I mean, this is sort of like typical of a research problem that you try to do something, you're like, okay, that's too hard, I'll do something else, and you do something else. And then somebody asks you, hey, but what about the thing that you wanted to do in the first place? Because we have defined an algebra structure or a division ring structure on R3, I mean, on R4, can you do it for R3? And it turns out that the answer actually is no. There is a theorem due to Frobenius, again, 19th century, but a little bit later, I think about 30, 40 years after these ideas were being considered, which tells us that the only finite dimensional division rings over R, in other words, the only sort of ways to define a vector space, I mean, a multiplication on a finite dimensional real vector space in such a way that you get a division ring and at the same time preserve the vector space structure are the three that we have seen over the last 15 minutes. That you have R itself, you have C, which is defining the structure of a division ring on R2, and you have the Quaternions. There is no other object. I mean, there's no other division ring apart from these three on any finite dimensional real vector space. So in particular, you can't do it for R3. The fact that Hamilton was struggling was not sort of a particular concern. It was a general obstruction. It does not work. The proof of this theorem is not particularly difficult, but do note that it actually, in some sense, assumes the fundamental theorem of algebra, namely that every complex polynomial has a root, because in particular, you don't have any extensions of C. Okay, that'll come up in a little bit. Okay. So that's kind of the non-commutative story. And it's interesting to sort of realize that the early origins of ring theory were dealing with these kinds of non-commutative number systems. But of course, mathematicians in the 19th century were also considering other objects. I mean, particularly those who were working in what we might today sort of call algebraic number theory or the theory of function fields, were working with, rings which we might consider to be, which are commutative. The integers, the Gaussian integers, polynomial rings. I'll spend a little bit of time talking about polynomial rings in a moment. So let's just briefly define them. Again, this is something that we may all be familiar with, but just to go over it, make sure that we're all on the same page. If we take any ring and we take an indeterminate, you can talk about polynomials over R, right? So polynomials formally are expressions of the form that's on the slide. Even more formally, we can just think of them as sequences indexed by the natural numbers, which are non-zero and at most finitely many coordinates, if you really want to sort of have a set theoretic definition of what these things are. And then we have an addition and a multiplication that, again, I'm sure many of us are familiar with. It just encodes the fact that you want your multiplication to be distributive over addition, and you also just want x into x to be x squared and so on and so forth. So polynomials over any ring form a ring. And something which is of particular interest is that they can naturally be viewed as functions. Right? So if you take a polynomial, in some sense, there's that indeterminate over there that's begging to have something plugged into it and evaluated at it. That if you take a polynomial with, say, real or complex coefficients, then we can think of that as a function from the real or complex numbers to itself. Namely, I take a complex number alpha and I evaluate the polynomial at the element alpha. The degree, this is for use later, the degree of a non-zero polynomial is the index of its highest non-zero coefficient. And again, just some terminology, we call polynomials of degree strictly less than 1 constant. Again, I suppose these are terms that are familiar. Now we can get used to them. Okay, so now we have a few examples of rings that were sort of historically relevant, right? Matrices, the Quaternions, the complex numbers, polynomial rings, the ring of Gaussian integers. And for more information about the history of these objects, there is this wonderful article by Israel Kleiner called From Numbers to Rings, the Early History of Ring Theory. It sort of sketches out how these ideas all fed into what we would today call the modern theory of rings. In particular, I mean, so we saw that the abstract definition of a ring emerged sometime around 1917. But there were, of course, theorems proved about these things without using that formal definition. Two names that are particularly relevant to the development of abstract ring theory are M.E. Noether, who we today might sort of know of in the context of Noetherian rings, who in some sense formalized the theory of commutative ring theory, and Emil Artin, who had a similar contribution for finite dimensional algebras, particularly non-commutative ones. That's Noether, and that is Artin. Okay, so that's the history. Let's spend the next 20 or so minutes talking a little bit about geometry. And by geometry here, I mean something very specific. I mean algebraic geometry and the links between algebraic geometry and ring theory. We've already, so before that, the study of commutative rings has evolved into a rich and beautiful mathematical discipline, commutative algebra. It is a rich discipline in its own right and also forms the technical foundations for much of modern number theory and algebraic geometry. One thing that we've already kind of seen, right, is that there is a connection between polynomial rings and geometry. If I have a polynomial in one variable or in many variables, I can talk about its set of, say, solutions, its zeros, which is a natural thing to do that we've all been doing. And that sketches out various associative subsets of, say, C or C to the n or K to the n, depending on what your field is. So to sort of rephrase that, there is a geometric space associated with rings of polynomials. If I take, for example, polynomials in two variables, C, X, Y, I can think of those as functions on C2, on C squared, by just evaluating a polynomial in two variables at a pair of complex numbers or a pair of real numbers. Now, one of the great, in some sense, developments of modern algebra was that it turns out that any commutative ring can be associated with a geometric space in such a way that elements of that ring can be thought of as functions on that geometric space, right? So this is taking us to the 1950s and the birth of modern algebraic geometry, which to a large part was due to the work of these two individuals, Jean-Pierre Serre and Alexander Grothendieck. What might be nice over the next 10 minutes is just get an insight into how we can think about rings that are not typically geometric in our understanding in a geometric fashion, right? So to do so, let's ask a simple question. What should be the geometric object associated with the integers? Which which at first glance, we might not think of as a geometric, as an object that has an associated geometry associated with it. And let's try and work by analogy. So I know that for polynomials, there is a geometry. Given a polynomial, even in one variable, I can think of its solutions in the complex numbers if my polynomial is defined over the complex numbers. So let's work with the complex numbers and let's work with the ring of polynomials in one variable over C. Why C? Well, C is a particularly nice field to work with because it is what we would call algebraically closed. In other words, you have the fundamental theorem of algebra, which tells you that if you have a non-zero polynomial of degree n, then it factors into not necessarily distinct linear factors. this is equivalent to saying that every non-zero polynomial, every non-constant polynomial over C has a root, which is something which is not true over R, for example. I mean, x squared plus 1 doesn't. And this makes the complex numbers particularly amenable to understanding, at least in terms of their algebraic structure. Okay. So remember that the geometric space associated with the ring of polynomials is just the set of all complex numbers. Let me minimize this. So one question to ask is, how can we reconstruct C from C of x? And I should emphasize that when I say reconstruct at this point, I really mean reconstruct as a set. C, of course, is a set which has a great deal of structure. It has a number of norms, topologies, metrics. I'm just talking about getting C as a set at this point. Well, one observation is that there is a correspondence between elements of the complex numbers and certain kinds of polynomials in C. I mean, there are many ways of doing this. I could think of a complex number as a constant polynomial. But another option, which tends to work, which actually works quite well, is to think of a complex number and associate it with the linear polynomial which has that complex number as its root. And in this way, we have a one-to-one correspondence between complex numbers and monic polynomials of degree 1. Okay? So we have, but again, the thing is that phrasing is using words like degree, right? It's using words like monic. So the question is there a way to rephrase what we've just done to isolate the set of monic polynomials of degree 1 using just the language of ring theory? So I can't refer to anything specific about the polynomial ring C of x, like its degree function, but something which is encoded in terms of the algebraic structure of C of x, its multiplication and its addition and so on. We begin by making an observation. Suppose P is a non-zero, non-constant polynomial, which has the following property, that whenever I write it as the product of two polynomials, then at least one of the factors must be constant. It follows from the fundamental theorem of algebra that if P were to satisfy this criteria, if P were to sort of be a polynomial, which we cannot write as a product of non-trivial factors, then it must in fact be some complex number into a polynomial of degree 1. In other words, the only polynomials that satisfy this definition are complex polynomials of degree 1. So there's a word for this which we all learned in our first ring theory class, and that is that the irreducible elements of the polynomial ring are precisely polynomials of degree 1. So in some sense, that what we have done is recaptured the idea of polynomials of degree 1 in the language of ring theory as precisely the irreducible elements of the polynomial ring. Okay? But the one, again, remember that we wanted monic polynomials, right? The correspondence that we had in the previous slide was between a complex number and a monic polynomial. Here, being irreducible is not something which is affected by multiplying by a scalar, at least a non-zero scalar. So how, again, do we isolate the monic polynomials in this? Well, one way to do that is to make a few more observations. The first is that what is it that distinguishes the constant polynomials, at least the non-zero ones, in the context of the polynomial ring? And it turns out that it is precisely that the non-zero constant polynomials are those which have a multiplicative inverse. In other words, again, what we have just observed is that the units, remember that in any ring, we can talk about the units, which are those elements which have multiplicative inverses. The units in the polynomial ring are precisely the constant polynomials. Okay, great. So what we can do now is reconstruct the complex numbers from C of x by looking at the set of all elements in C of x which satisfy the property mentioned a couple of slides ago, namely that it is all non-zero polynomials which have the property that if you can write them as a product of two polynomials, then at least one of those two must be a unit, as long as we identify those elements which are scalar multiples of each other. So more formally, we define an equivalence relation on the set of all irreducible elements of C of x by setting two polynomials to be equivalent if and only if there exists a unit B such that P is equal to B into Q. In the language of ring theory, what we say is that these two irreducible elements are equivalent if they are associates. And what we have just observed is that equivalence classes of irreducible elements, where the equivalence relation is the one that was mentioned right here, are precisely parametrized by the elements of C. So to summarize, irreducible polynomials, to summarize, we can recover the elements of C in some sense by looking at equivalence classes of irreducibles, where the equivalence relation is that there is some unit which upon multiplication by that unit goes from one to the other. The final observation worth recording is that irreducible polynomials are equivalent if and only if they generate the same ideal. Again, that's something that'll come up a little bit later. Okay, so what we have done is that we have recovered the complex numbers from the polynomial ring C of X. But what happens if we try and carry out the same process in Z? So the units in the integers are well known, plus minus 1. The irreducible elements in the integers, again, also well known, are precisely primes and their negatives. Again, so we sort of see that a prime and a prime multiplied by a unit. And what that tells us is that equivalence classes of irreducible elements are parametrized by primes, which suggests then that maybe the candidate for the geometric object that we want to associate to Z is the set of prime numbers, right? So if we do exactly what we did for C of X, over the integers, the object that we get as the candidate for the geometric object associated to the integers is the set of primes. All right. But we have our candidate geometric space, the set of all prime numbers. But remember the important thing about polynomials, right? It wasn't just that there was a geometric space associated with the ring of polynomials over the complex numbers, but that a polynomial over C was a function on that space. So our question now is, how do we think of elements of Z as functions on the set of all primes? Right? Because unlike a polynomial which sort of has an indeterminate, which is begging to be evaluated at a point, it's not obvious how you might evaluate, for example, the number 17 at the prime 23, or the number 36 at the prime 2, and so on. So again, what we do is we proceed by analogy. And what we want to try and do is in some way recover the action of a polynomial on the set of complex numbers through the ring theoretic structure of the ring of polynomials. In other words, we want to somehow recover the fact that the value of a polynomial P at a complex number alpha in terms of the ring theory, not in terms of thinking of the polynomial as something that we can evaluate. So one strategy that suggests itself is by using just classical division. I think in a first ring theory course, we all learn about the division algorithm, which tells us that if I have elements of the polynomial ring C of X, where P of X is not equal to 0, then it's possible to, in some sense, long divide. I can write Q of X as the product of P of X with something plus a remainder term, where that remainder term is either 0 or the remainder has degree, which is strictly smaller than the degree of what you're dividing by. Sorry, there's a typo over here. There should be that the degree of R of X is strictly smaller than the degree of P, not the degree of Q. And that is a typo. Apologies. Okay, why is this useful for our purposes? Well, suppose I take a complex number alpha, and let's consider the corresponding degree 1 monic polynomial, which has alpha as a root. Given a polynomial Q of X, we can apply the division algorithm to find a polynomial S of S in C of X of some degree, and a complex number R such that Q of X is equal to S of X into X minus alpha plus R, right? Note that because in the division algorithm, the remainder term has to have it has to be of degree strictly smaller than the degree of what we're dividing by. In this case, we're dividing by something of degree 1, which means that the remainder term has to be degree 0 or has to be 0 itself. So either it is 0 or it is going to be some non-zero complex number. Either way, it is a complex number. And then we can express q as a multiple of x minus alpha and some complex number. If we evaluate the above expression at alpha, what happens is that this linear factor disappears, and we precisely get that the remainder is what we would get if we were to evaluate the original polynomial q at the term alpha. In other words, what we can do is we can recover the behavior of q as a function on the complex numbers purely in terms of the ring theoretic structure of the polynomial ring. That we take a complex number alpha, we look at the associated linear monic factor x minus alpha, divide q of x by x minus alpha, and that remainder term that appears is exactly what we would get if we had just evaluated q of alpha to begin with. And then this suggests a way to proceed in general, right? Because now I also have a division algorithm for z. If p and q are integers, and p is not equal to 0, in this case, I think I've got it right, yes, then you can find elements R and S and Z such that in this case, the degree is that we have for polynomial rings is just replaced by absolute value. We can find some element whose absolute value is strictly smaller than that of what we're dividing by, such that I can write q as a multiple of p plus that remainder term. So proceeding by analogy, if I want to now if I now start off with an integer n and a prime p, remember that under our dictionary, the geometric object that we are thinking of associating with the integers is the set of prime numbers. So now if I take an integer, how do I think of it as a function on the set of prime numbers? Well, what we can do is we can evaluate n at the prime number p by taking the remainder when we divide n by p. Because that is exactly what happens and what gives us the correct answer when we're working over the polynomial ring. So in this sort of model, what we get is that the roots of an integer n, in other words, would be what? Well, they would be the prime numbers, such that when we evaluate n at p, we get 0, which in this case means 0 remainder. And thus the roots of an integer n would be its prime factors. Actually, we are doing a little bit more in this example. We don't want to think, we want in some sense the values of whatever function n is representing to take values in a field. So when we take the remainder after dividing n by p, we think of this number as living in the field z mod pz, not in the integers. Okay. But now we, in some sense, have a model for what it means to think of the integers as functions on a geometric space. The geometric space is a set of prime numbers. An integer evaluated at a prime number is just calculating in the remainder upon division by p. And it turns out that this actually works and gives you a sensible theory. Extending the above approach to more general commutative rings requires a lot of work and quite a bit of technology. So just briefly, I won't go into the details of this. I'll do a few examples. I'll describe a few examples later on. What we can do is associate every commutative ring with something called its spectrum. And its spectrum as a set is the set of prime ideals of R. So remember that an ideal of R is said to be prime if whenever the product of two elements is in the ideal, one of those two elements is in the ideal as well. And it's also not equal to the entire ring. It's a fact that you might have seen in a first algebra class that because the integers and the polynomial rings are PIDs, there is a bijection between equivalence classes of irreducible elements, namely the equivalence relation being that two elements which are irreducible are equivalent if they differ by a unit. And there's a bijection between these equivalence classes and non-zero prime ideals. So in some sense, what we were doing previously for the polynomial ring and for the integers was associating these rings with the non-zero prime ideals that they have. Here, you'll notice that we've not restricted ourselves to just the non-zero prime ideals. We've said that Spec R is the set of all prime ideals. So for example, in both of the examples mentioned over here, 0 is also going to be there. That's useful. That's useful for technical reasons. In fact, it's required to make this a nice operation. But even in like relatively nice examples, you still need to change the way you think about things. Right? So fine, over the complex numbers, when we were working with C of x, we looked at the associated geometric object and we just got the complex numbers back, apart from, well, this 0 issue, but that's minor. But even over the real numbers, something changes, right? Or if you look at the prime ideals in the polynomial ring over R, then you will be getting irreducible factors that are not linear. The ideal generated by x squared plus 1, for example, is prime, but it will not correspond to a unique real number because, well, it doesn't have a solution in R. So you sort of get more points than just the elements of R, but that should not be viewed as a defect. It's sort of viewed as correcting the fact that R is not algebraically closed. So you needed those points, they just weren't there to begin with, if you looked at this thing naively. Okay, so the next slide is just to give you all a glimpse of how this theory develops. If you don't know the language, then feel free to ignore it. It's the only time you're going to see these terms, apart from the last slide. Which is that, in fact, this set that we've described, the spectrum of R, has more structure than just a set. It is something called a scheme, and in particular, it carries a topology. If you don't know what these words mean, that's fine. The importance of this second statement is that in some sense, the operation of taking a ring, a commutative ring R, to its spectrum is one in which you don't lose any information. That by building this geometric space associated to your commutative ring and looking at this geometric space along with the structure that's defined on it, you don't lose any information about the ring, and that you can think of the rings in a purely geometric fashion if you want, and you are not losing anything. That's what this statement is saying, that the spec as an operation is actually a contravariant functor from the category of commutative rings to the category of schemes, and this functor is fully faithful. Again, if you don't know what these words mean, not an issue. They won't come up again, except in the very last slide. Let's see some examples. So the first 3 examples are essentially saying a fact that many of you may have encountered, which is that the only ideal, the only proper ideal in a field is 0, right? Because if anything is, if you have a non-zero ideal, then it must contain a non-zero element, and upon multiplying that by its inverse, you get 1, and therefore you get everything. At this point, you might say, okay, wait, something is a bit strange, because you just heard that taking the spectrum of a ring should not, cause you to lose any information. But here you're sort of getting the same set as a spectrum for Q, R, and C, which are not isomorphic as rings. So that's where this sort of additional structure of being a scheme comes into play, right? So the idea of the additional structure is that it allows you to sort of then say that, okay, fine, the spectrum of Q, which is a single point, along with that structure, precisely pins down Q. Even though just as a set, the spectrum of Q doesn't. In fact, even as a topological space, the only topology that we can have on a singleton set is where the open sets are the empty set and the entire space. So as topological spaces, these 3 are also the same. So it really is that additional structure which is allowing you to recover the ring from this object. The spectrum of R2, where R2 is given the pointwise operation, is not too difficult to sort of describe. Essentially, the only 2 prime ideals there are R cross 0 and 0 cross R, which are what are generated by 1, 0 and 0, 1. It's a fact, which is a nice exercise if you've just started learning commutative algebra, that if you look at power series as opposed to polynomials, then a power series is invertible if and only if its constant term is non-zero. What that tells us is that the only prime ideals in a power series ring over, say, in one variable over the complex numbers, that should be a boldface C, are 0 and the ideal generated by X. In this case, though, what's important to note is that even at the topological level, the spectrum of the ring of power series in one variable over C and the spectrum of R2 are different. As a topological space, the spectrum of R2 is essentially discrete. Both of these points are open. The spectrum of C of the ring of power series in one variable is not discrete. The point corresponding to 0 is closed, but is not open. So over here, the topology also distinguishes these things. And then the last two examples here are the ones that we talked about earlier, that the points that we might associate to the geometric space that we would associate to the integers would be the prime ideals along with 0. And the points that we would associate to, say, a polynomial ring in one variable of the complex numbers are just essentially the points of C, but here thought of as corresponding to the unique, we associate a complex number with the degree 1 monic polynomial having that complex number as a root, again, along with 0. You might ask what happens for, say, polynomials in two variables. It's a natural question. The picture is pretty much what you would expect. And in some sense, proving what is on this slide rigorously is, in many ways, the aim of a first course in commutative algebra, because there's quite a bit of foundational commutative algebra encoded in the statement that's on this slide. So what we're saying over here is that if you look at the prime ideals of a polynomial ring in two variables over a field, and again, sorry, the C should be the boldface C, then they kind of come in three kinds. You have 0, which is a prime ideal because the polynomial ring Cxy is an integral domain. For every irreducible element, by irreducible, I mean it in the same way that we meant it earlier, that if you were to write it as a product of two things and one of those two things must be a unit, the principal ideal generated by that irreducible element is also going to be a prime ideal. In some sense, that's reflecting the fact that the polynomial ring Cxy is a unique factorization domain. And then for every element of C2 now, remember that the prime ideals of Cx were in some sense given by elements of C along with 0. Here, for every element of C2, we have an ideal generated by x minus alpha, y minus beta. And that gives us an ideal which is maximal and therefore prime. Now, again, proving that the spectrum of C of x in one variable was given by by elements of C and 0, that was not very difficult once we knew the fundamental theorem of algebra. This statement on the slide actually requires more work. In some sense, the fact that the statement that all of the prime ideals which are maximal are exactly those of the form x minus alpha, y minus beta is this theorem called the Nullstellensatz, specialized with the case of Cxy. The fact that these are the only prime ideals in the spectrum of Cxy also requires developing some theory, some dimension theory over Noetherian rings. So yeah, it's a plausible statement, but understanding this in some senses would require a first course in commutative algebra. And in many ways, the theorems that you will learn there will help you rigorously understand what's going on over here. Okay, in the last 5 minutes or so that I have, I wanted to just briefly talk about the area that I work in, which is non-commutative ring theory. So this is a brief glimpse of the commutative theory. And remember that our talk began with a non-commutative example. The theory of non-commutative rings displays behavior that might seem very pathological from a commutative perspective. Now, that should not be unusual. I'm sure when you all learn group theory, for example, you learned that the way non-abelian groups behave is very different from the way abelian groups behave. So it's not unexpected, but the kind of phenomenon that you might witness in the non-commutative world is still something worth observing. It's interesting. As a first example, one thing that's implicit when we sort of study polynomial rings over a field is that if you take a polynomial, right, then it can have at most as many roots as its degree. If I were taking the polynomial x squared plus 1, and we're looking at its roots in a field, I know that it can have at most 2 roots. I mean, there are, in the complex numbers, this would have 2 roots, and over the real numbers, it would have none. So, but you can have at most 2. Over, say, the field with 2 elements, it would have 1. It would just repeat itself twice. But if we go to the Quaternions, and remember the Quaternions are a division ring. So they are pretty much, I mean, so you have inverses. You just don't have commutativity. If you remember the defining equations for the Quaternions, you had I, J, and K representing 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. All 3 of those elements square to minus 1, which means that all 3 of those elements would be roots of this polynomial P. So you have a polynomial of degree 2, which has at least 3 roots. In fact, the situation is far worse. If you take any element in R3 of norm 1, and you think of it as an element of the Quaternions by thinking of it as corresponding to the element in the Quaternions, which has 0 as that scalar entry and your element V as the corresponding vector in R3, and you think back to what multiplication was in the Quaternions, right? Then 0 comma V into 0 comma V would essentially be minus the norm of V squared comma 0, because the cross product of V and V with itself is 0. And here the scalars are both 0. So you don't get any, there's no contribution in the R3 term, and you just have a minus 1 popping up. So what we actually see is that in the Quaternions, which is in some sense one of the simplest examples of a non-commutative ring, you already have a dramatic failure of some fundamental facts from the theory of commutative fields. That you have a polynomial of degree 2, which doesn't just have more than 2 roots, and in fact has uncountably many. Any point in any vector of norm 1 in R3, suitably interpreted in the Quaternions, would give you a root of this polynomial. Okay, that is just one glimpse of interesting phenomenon that you don't see in the commutative world. When you start thinking about non-commutative things. Another example is from matrices. So the next 2 or 3 slides are just, the next 2 slides are just examples. They're just sort of pointing out things that don't work the way you might expect when you start working with non-commutative rings. The last slide contains what I think is a fascinating theorem, which not mine, is due to somebody called Manuel Reyes, and we'll mention that. I'll mention very briefly when we come to it. So if I have a field F and I look at the ring of n cross n matrices over F, and let's call that M and F, it's an easy exercise to show that the only ideals in M and F are 0 and the ring itself. Essentially, that's just an exercise in playing around with elementary matrices and multiplying by doing the row operations and column operations. It's quite straightforward. In other words, we have a word for this. The rings whose non-zero rings whose only ideals are 0 and the entire ring are called simple rings. So the ring of n cross n matrices over a field is a simple ring. Which means that in particular, if you look at the ideal generated by 0, it's a maximal ideal. Now, one fact that we learn when studying ring theory is that maximal ideals are prime. However, over here, if I just take, for example, the following 2 elements of M2F, multiply them, they're both non-zero, their product is 0. So all that example is telling us is that we need to modify our definition of a prime ideal. Because, yes, you do want to have a notion of a prime ideal for rings in general. And whatever that notion is, you do want maximal ideals to be prime. So it turns out that the definition that works in the non-commutative context is to replace elements by ideals. It's an exercise to show that this is equivalent to the definition, to the element theoretic definition if you're working over a commutative ring. But we say that an ideal P in a ring R, where R is not necessarily commutative, is prime if it's proper and given ideals I and J, whose product is contained in P. Either I is contained in P or J is contained in P. Okay? And if we use that as our definition of a prime ideal, then yes, 0 is going to be a prime ideal in this context. So that works. But another problem arises, which is that second pathological example. Let's again stick with the field and consider the following inclusion of rings. So here I'm taking 2x2 matrices over F, and I'm looking at the subring consisting of those matrices which are 0 off the diagonal. So on the diagonal, the elements can be whatever they want from our field. Off the diagonal, you're necessarily 0. Now, it's a fact of fundamental importance in commutative algebra that if I have a homomorphism of rings from a ring R to a ring S, and I take a prime ideal of S, and I look at its inverse image under that homomorphism, what I get is a prime ideal in R. In other words, inverse images of prime ideals are prime ideals. In fact, that in some sense is what encodes the functoriality of the spectrum construction. Let's see what happens here. So remember that we were forced to define prime ideals in this ideal-theoretic way because we wanted a ring like a matrix ring to have prime ideals. In this example, we know that in M2F, 0 is prime because it's maximal. But this map phi is injective. So when I look at the inverse image of 0, I just get 0. But 0 is not prime anymore, viewed in F cross F. Because in F cross F, what I can just do is essentially took the examples that we had from the previous slide, but now here they actually become ideals, and observe that this product is 0, but 0 is itself, so therefore 0 is not a prime ideal. And that kind of tells us that defining primes the way we have are no longer functorial. And that's a big problem, right? It sort of really makes developing a geometric theory for non-commutative rings quite difficult. You might ask whether that is a problem with our particular construction, that maybe we weren't clever enough, or there's some other definition that we should be using. And if we were to use that other definition, then things would work out in a slightly better fashion. It turns out that the question of what the spectrum of a non-commutative ring should be is one of genuine difficulty. Over the last 50, 60 years, there have been several candidates. None of them are perfect. I mean, you can there have been attempts to build candidates using the ideal structure, using the module structure, and they all have some defect or the other. And there's this wonderful theorem that was proved maybe 10 or 15 years ago by Manuel Reyes, which actually again tells us that the obstruction to developing a non-commutative theory which works is not one for lack of trying, but there's a fundamental problem. And that is that you can't do it. That if you did have some way of associating rings to sets, so like, for example, taking a commutative ring to a set of prime ideals. So if there was a functorial way of doing this for all rings, right? If you had a contravariant functor from the category of rings to the category of sets, whose restriction to the category of commutative rings is exactly the classical spectrum construction, then such a functor must necessarily send all matrix rings of suitable size to the empty set. And that is extremely unsatisfactory because you don't want non-zero rings to have a non-zero spectrum. So the question of how to repair this is one that is, very interesting, and in some sense is a motivating question for a lot of modern non-commutative ring theory. Okay, I think I am out of time, so I'll stop now, and I'm happy to answer any questions that people might have, or to go back and go over any part of the talk that might need further elaborating.
Plus something like the slide you showed, that structural group kind of thing. Would you show
Which
that
slide?
again? You put some topic like structural group and all, something starting with this. I'm asking very vaguely, but I couldn't recall the slide. So
Was it
in the middle portion, like I think, yes.
this one?
This one, right?
Okay.
Right. Just like how like in geometrical aspect, how we visualize the speaker and on the field of complex numbers and also
Sorry, is the question how you might visualize the spectrum of the ring of polynomials in one variable over R?
one variable or multivariables kind of thing. Yes, yes.
I mean, multiple variables, when the field is algebraically closed, I mean, it's still not straightforward. Like, for example, for two variables over the complex numbers, essentially the spectrum is the set of points in C2. And then for each irreducible algebraic curve in C2, you have a point. So irreducible algebraic curves themselves are points of the spectra. And then you have a generic point 0, which has the entire spectrum as its closure, which sort of makes it compact. Over R, I don't know. I mean, so the spectrum of R of X, in some sense, one picture that might work is to think of it as the upper half plane, where you have the real numbers on one side
Yes, yes.
corresponding to ideals
I
of the
was also
full.
thinking the same. Sorry to interrupt. I also thinking the same, like upper half plane, right?
Yes, and then you sort of identify a complex number and its conjugate, and as corresponding to the irreducible polynomial that they're both the roots of.
Okay, okay.
Do anybody else has to ask anything? Okay, so if there are no questions, thank you so much, sir. It was a wonderful session. Now we'd like to proceed for a group photo, and I'll request everyone to open their cameras.
Can I stop sharing?
Yes, sir.
Okay, great.
Okay, so on the count of 3, I'll take the picture. 3, 2, 1. Smile, please. Yeah, it's done.
Thank you again. That was fun.
Thank you so much, sir. It was a wonderful